Thanks for introduction. My name is Karol Gugala, and as it was said, I'm going to tell you a few words about accelerating AI processing on the edge. I'm from Antmicro, and I would like to introduce myself and the company maybe, so you can have overview of what we do and why we do stuff, and then you that will enable you to better understand what we did and why we did it in the end. So Antmicro is a technology company. We're basically working on developing new technologies in various areas of everyday's life. We are software driven. It means that even if we are doing things hardware related or hardware itself, we still use all the methodologies that are commonly used in software development, meaning like CI and test-driven development and all those things. One important thing about us is that we use open source wherever we can, and we don't really like to be tied to any specific vendor or any specific technology that we use anywhere. Not only do we use open source everywhere we can, we also actively contribute to open source ecosystem. We are members of world leading open source organization. Probably Linux Foundation. That's one of the biggest and best known open source organization in the world. But we're also a member of Chips Alliance, which targets to build open source hardware in terms of like ASICs and chips in general. Zephyr project, which is in fact part of Linux Foundation, also RISC-V Foundation, that is basically holding and carrying of RISC-V ISA, which is a CPU architecture specification. We're actually one of the founding members there. We've been with this technology, with this movement from the very beginning. If you are interested what we do in the projects we do, you can visit our website. We have something called Technology Showcase there, where we present projects we did, technologies we do, and you can just read articles about it, follow the links to source code, grab it and play with it. And if you are interested in our open source projects, we last year we launched our open source portal at opensource.micro.com. There you can find I'm not saying all, I want to say all, but most of our open source projects that are released somewhere, so you can get them in a single place with links to repositories and all those things. So getting back to the topic of my today's presentation, I would like to start with explaining the term Edge AI. Maybe some of you know that, but if you don't, this term is basically used to describe AI processing or machine learning processing done on a smaller devices that are really close to the sensors. And by sensors, I mean all those things like video cameras, but also microphones or temperature sensors, accelerometers, and all those things. Basically, you process the data as soon as you get it from the certain device that can digitalize the surrounding world. What is the difference between edge and cloud processing? So probably cloud. I mean, the AI processing, machine learning processing in cloud is very common. We typically use a very bulky machines there, put somewhere, they are placed somewhere in a server room. We don't really see those machines, so we just remotely feed them with data. We run some algorithms there, get the results, and we're happy with that. In a cloud system, we virtually have unlimited resources. I mean, virtually, because if you are using things like Google Compute platform or Amazon services, web services, you can easily extend the machine that you're using with additional CPUs, with more memory, and all those things. Yeah, so virtually we have, I would say, unlimited resources there. But the problem with that is, first of all, we have to send the data and receive it back. So we have, high latency of processing. So if you need real-time processing, something that requires, reaction or decision immediately when the data comes, that's not really usable. Plus, the machines are pretty big. You cannot really deploy them anywhere. They consume a lot of energy, so that's not really usable in some mobile systems or like autonomous system. But they are great for example, training algorithms, because training requires a lot of processing power. Edge devices, on the other hand, are smaller, so they often, I mean, they require less energy. They can be placed, they can be put into in some machines, remote machines, or into some autonomous devices that can actually hold this smaller device. But with the size comes also less processing power, so you cannot really run as complicated or as big AI models or as complex machine learning algorithms on those smaller devices. And since training is require a lot of resources, edge device is not really good for training. You can do that, but of course it would take ages to train even simple model. But they are really effective when we inference one trained model. So why do we actually need edge AI? So some of the reasons, I actually mentioned some of the reasons. Sometimes you have to process the data as soon as you get it. Yeah? For example, you have some kind of a vehicle that have to react as soon as it sees an obstacle. You cannot really send this data to a cloud, process, and get it back, because probably at the moment when we get back the results, we're actually hitting the obstacle, or even worse, we did something really bad. But the AI is also small devices. Yeah, small devices, I mean, like smartwatches or some home assistant device. Yeah, something that is sitting on our table, and we can just shout at it and it will start doing things. This is also edge AI, and we need those to make our lives easier, to have fun, and basically solve problems that we cannot really easily solve with a bulky machine somewhere in a server room. So what are the use cases of edge AI? As I said, autonomous vehicles, but also medical devices like portable scanners. We actually even worked with such a device. And if you go to our webpage, you can find a story, a use case described in details, where we helped build a portable skin scanner, where you could use a device to a physician, a doctor can actually use this device to scan patient skin and mark any skin changes that are potentially problematic. Also, edge AI devices are used in product quality inspections, like on production lines, and all those things where you cannot really put a bulky machine. So also, in let's say very dirty and dusty environments, where you cannot put a machine that consumes a lot of energy and requires a lot of cooling, because you cannot have active cooling in a very dusty environment. Okay, so it sounds like it all sounds really, really nice. So what's the problem? What are the problems we're facing when working with edge AI algorithms and edge AI devices? To explain that, let's start from looking at typical machine learning or AI deployment flow. So we typically start from choosing or preparing model architecture, basically our deep learning or the neural network architecture that has to process the data that we want. There is a lot of ready to use models, or we can propose a new one. That's pretty, that's pretty obvious what to do here. Of course, we need some kind of a data set that we then use for training. So once we have a model, we train it, then evaluate, then optimize and compile, and we repeat those three steps until we're happy with the results. Once we're happy with the results, we want to deploy the model on a hardware and run it there. So what is this hardware? What can we actually use when we are talking about edge AI targets, edge AI processing? So some of those are actually very similar to what we have in server rooms or in our desktop PCs. So those are GPUs or CPUs. Of course, the GPUs and CPUs on edge devices are smaller. They are not as powerful as the ones we have in desktop machines or in server machines. But a lot of edge AI devices have dedicated accelerators that can be used and utilized for accelerating the processing. Those are tensor processing units from, for example, tensor processing unit from Google. NVIDIA released, designed and released something called NVDLA. Again, accelerator that can be used to speed up the processing. VTA, an open source accelerator that can be deployed in FPGA or in ASIC. Our mobile phones, they all have right now, all the CPUs there, all the SoCs there have dedicated accelerators to speed up processing of the algorithms we run on our mobile phones. And of course, microcontrollers that we small microcontrollers that we can use in like smartwatches and things like that. Yeah, so they consume, they are very energy efficient, but don't have really much processing power. So to handle that, there is a lot of frameworks, AI and machine learning frameworks that can where we can design a model, build it, optimize, and compile for the target hardware. That looks pretty nice. I mean, sounds like, okay, we have a choice. That's great. So what's the problem here? And I listed a few of them here, but that's not all of them. There is way more open source frameworks and even more proprietary ones. Those are the listed ones are open source. So we have a lot of frameworks. So what's the problem? So the problem is that this is very, very, the whole ecosystem is very diverse. All the frameworks, they do more or less the same. They allow you to create a model, to design a model, to use certain operators, certain layers in your AI model, then optimize it and then compile. But they all use different data structures. They all use different data types inside. So you cannot really easily switch between them. And even worse, certain hardware, so certain targets, certain hardware targets with accelerators support selected frameworks. So once you select a framework, you're kind of tied to a hardware, to target hardware, or if you select a target hardware, you tied to a framework. So you have a problem of, I would like to use, let's say, NVIDIA Edge AI devices, so I have to use only the framework supported on those that support this hardware. Otherwise, I would have to run. I cannot really, if I use a different framework, I cannot really utilize the accelerators. So processing is really slow and absolutely unusable. So as I said at the beginning, we are at Micro. We don't really like to be tied to a certain vendor, to a certain technology. We like to have freedom of that, and we don't really like to be forced to stay with certain technology for ages because we did some choice like a few years back. Like we did a choice of certain framework, and then we have to stay with the hardware. We cannot really migrate it. So what can we do about that? So we started analyzing those frameworks, and in the end, um, as it was expected, it turned out that they all do more or less the same. The only difference is the way the data is stored, the way the data is sent back and forth between different processing of different deployment steps. So why not introduce something that would allow us to easily exchange the frameworks, easily switch between the framework we develop the model with and the target hardware in the end. So there is no such tool on the market. So we had to create one, and we created a framework called Kenning. And Kenning is an open source framework implemented in Python. You can find it on our GitHub, and of course, it is listed in our open source portal. So Kenning wraps various machine learning and AI frameworks in a way that you can easily exchange the models and easily transform model from one framework into another one. So you can use, let's say, for example, TensorFlow to develop your model, and then in the end transform it to TVM and deploy on a VTA accelerated hardware. Yeah, so that one actually solves the problem of I did my choice in the past, and I have to stay with that. So Kenning has a few blocks. Those are dataset, model wrapper, model compiler, runtime, and runtime protocol. And this allows you to basically do all the cross conversions between the frameworks and passing the model between them, optimize the model, deploy it on a hardware, and even measure its efficiency. So here is a more detailed view, and in green we have a path of deploying the model. So when we have a model and we want to simply run it on a selected hardware, feed it with data, and grab the results. So then we follow a green path. Basically, we just have to cross convert it into the selected framework and deploy on a hardware and basically use it there. The red path is the whole conversion and optimization for the selected framework, for selected hardware. So we start with a model in framework A. We run it through all the optimizations of compilation and so on and so on, and at the end we can deploy it. On a selected hardware. We use ONX or NNX, Open Neural Network Exchange Format, as an intermediate representation in Kenning, and that one allows us to do all those conversions and all those tricks with using various models from various frameworks on various hardware. The white part, the white blocks in this picture represent our monitoring functionality in monitoring and benchmarking functionality in Kenning, which is also a very nice feature because that one allows us to easily and fast benchmarking of the selected models on a selected hardware. So we can finally grab a model from any supported framework, run it on any supported hardware, and see which one is actually better. That wasn't really that easy before we created Kenning, because as I said, each framework, each hardware was supported by different framework. So doing an apple-to-apple comparison of a certain model wasn't really that easy, because on one framework it was really accelerated, on the other one it wasn't. So it was really unfair to compare accelerated inference with unaccelerated one. Yeah, so that wasn't really giving us an apple-to-apple comparison. So the whole benchmarking and monitoring flow can automatically generate reports. And in this slide, you can see images generated directly from Kenning. So you get things like that. Those are pretty basic. In this slide, we can see pretty basic monitoring options, like how much memory did we use, how much GPU memory did we use, how much time did it take to process the data, and so on, so on. So we can grab all this basic stuff to just know if how the model performs. But also we can do things like this confusion matrix, where we actually can check how classification, how a neural network doing classification performs. So we can see, not sure if that's visible in the stream, but those numbers actually tell if for a given object in an image, how was it classified. So as you can see here in this example, on the diagonal, we have the most hits, which is good, because that means that the object was actually classified correctly in most cases. But we have some confusions in the other places of the matrix, telling that we still have problems with some misclassifications of a certain objects here for this tested models. Also, we can, of course, we can check things like we can monitor things not only for classification, but also for object detection, instance segmentation, and so on, so on. So we have measurements for various types of models that we can deploy. And here again, another example of IOU. Yes, so AOU metric for object detection and an instance segmentation model. Yeah, so those are generated automatically from Kenning when we run various models on selected hardwares. So what Kenning gives us, first of all, it gives us the possibility to run and cross-convert models from implemented in various frameworks and run them on any of the supported hardware, which means that we finally can drop the vendor, drop what vendors want us to do, want to do with us. We can free ourselves from being locked within certain vendor ecosystem. And the other thing that the other very, very important aspect of Kenning is that it can benchmark things, and it can finally do apple-to-apple comparison of a certain model running on a selected hardware. And this can give us information of what we can actually use. And especially nowadays, when there is actually this whole shortage of everything, I would say, it's not that easy to buy as many devices or as many modules, processing modules, or chips that we can use for edge devices. With Kenning, we can actually check if our model can be used somewhere else and how it would perform. One thing that we're actually doing right now, because we are one thing that we're we are constantly upgrading, we are constantly contributing to Canning and adding new features. One of the things we started working on is combining various optimization flows from different frameworks. So because during our analysis, it turned out that various frameworks can do different optimizations, and while one of the framework, for example, can is very good at trimming. The other one can do other optimizations like let's say switch to is better at changing the I forgot the word. The resolution of the bit resolution of various numbers, like for example, converting the network from float to int8 to speed it up. And possibility to combine those optimization flows from various networks can give us in the end the ultimate optimizer that can do almost everything. So if you are interested in things like that, you can join us. We're looking for interns. I know that the most of the audience is actually students, so we have internship offer for people like you. So if you are interested, you can visit our webpage and see what is there. We can offer like summertime internships, those intensive internships where you spend like full day working on cool projects, or program that you can where you can work and study at the same time. So there is a flexible hours when you can just work on very, very nice projects. That's all from my side. Thank you. And I see there is at least one question for me. I'll try to answer that. If you have more questions, please ask them in a chat window.
Hi, Karol. Hi once again. Awesome. Your presentation was super interesting to us, and cool to see that these technologies are being built in Poznan. That's always awesome thing. Yeah, there are actually 3 different questions. I think the most upvoted one was from Wizal, and Wizal asks, what are the examples of hardware-specific optimization techniques, and which areas you were focusing on in optimization?
Mm-hmm. So these hardware-specific optimizations are mostly to convert the model to utilize the accelerators available on the hardware. So those accelerators that I mentioned in one of my slides, like tensor processing units or NVDA and all those things. So they require input data to be organized in a certain way so they can process it. They also often require the model itself and the data to be quantized in a very specific way, like NVDLA can process only int8 and int16s, nothing else. So if you have a model developed in, let's say, TensorFlow, and you have and you use floats there, you cannot really easily. I mean, you cannot use it with NVDLA. So you have to optimize it like that. You have to quantize. You have to reorganize the data that actually those accelerators can. In a way, those accelerators can edit, and basically that's when it comes to hardware specific optimization. Of course, there is a bunch of optimization techniques that are generic, I would say, like neural pruning, like connection pruning, and all those things. Yeah, so this is not really hardware specific, but also used very, very often in when you want to run on a smaller hardware.
Mm-hmm. The second question, I think that's a kind of a follow-up to what you already discussed. Casper asks, how does Canning handle hardware-specific differences, for example, Arduino versus SparkFun boards?
Mm-hmm. So we have, as I said, we use ONCs as an intermediate format. So basically, the flow is we have uh, quite abstract layers the layers that I showed are quite abstract, and they have of course specific implementation for various hardware. So in the end, when you choose, I would like use this framework with this hardware. Kenning can automatically connect the steps that are required to cross convert the model from A to B, basically, using ONCS as an intermediate representation, and perform, of course, the required all the required optimizations. Plus, allows you to add some optional optimizations within the flow. So it does like that. I mean, in the end, you have to have a specific specific backend for a certain hardware. Because of the differences, yeah. But Kenning allows you in the end to forget about it in some way. You don't really have to think of the target hardware from the very beginning.
Mm-hmm. And the last question is from Adam. What was the biggest challenge in developing this framework? And I also would like to, from my side, add who came up with the idea of developing it? Was that some kind of a natural thing that came from your work? Yeah,
Mm-hmm.
that would be
Yeah.
my
So
Adam.
yeah, let's start from the biggest challenge. The biggest challenge is, of course, each framework and each hardware requires certain has its own representation of things, and sometimes they are in most cases like 99% is compatible. You just have to cross convert it, so that's easy. But there is a bunch of corner cases, like certain frameworks implement operators that are not implemented in the same way in the other frameworks. So if you want to cross convert it, you have to replace, for example, one operator with two different operators in the other framework. So I would say the answer is pretty cliche. Corner cases was the biggest challenge, as everywhere in computer science. Corner cases are the killers. But ensuring that we can convert model from framework A to framework B without losing what model was supposed to do and losing some accuracy and all those things. And how did we come with an idea? We were working on various projects, on various hardware.
Mm-hmm.
We really work with whatever hardware is there, because as long as it does the job. Yeah. So
Mm-hmm.
if we want to, you know, process, do segmentation on the fly, whatever is there, whatever works, is good enough. And the problem was that, if you start with A, you have to continue with A, because you cannot really easily switch. You can do that. You could do the switch, but it required a lot of work, and nobody wants to do that in the end, because if you tell somebody, like tell your client that okay, I can migrate your awesome project from platform A to platform B, but it would take like half a year of work. So most of the clients say, no, no, really, I don't want to do that. And the other thing was that we often have questions like, I would like to do that. I have this input. I have this data that comes through this interface. Which platform should I use? And let's say if the interface is like, I have a camera connected over MIPI CSI, there is a bunch of platforms that can handle that. But which will be the best to process it? And the question is not that easy. I mean, you have to run the same like proof of concept on various hardware, and it wasn't that easy to actually do this comparison in a fair way. Because if I run it on, let's say, NVIDIA platform with GPU acceleration, it will be really fast and awesome. But then I'm using Qualcomm platform, but I cannot use the accelerator, and so I basically run the whole stuff on a CPU. It's slow, but if I would use the accelerator, maybe it's better than NVIDIA. We don't know that. We didn't know that, so that's why we came with a framework that can actually enable us to compare, enable us to run this comparison in a way it is fair, and in a way it gives us like scientific answer to the question which platform is actually better in this case, in this use case.
Awesome, Karol. Thanks for your contribution. Awesome to see you here at Ghost Day 2022. And thank you very much.
Great to be here. Thank you.
Thank you.